In a previous video, we showed that for an ideal gas, that delta U, the change in internal energy, was equal to 3/2 times the number of moles times the gas constant times the change in temperature, which is to say that for an ideal gas, the internal energy is only a function of the temperature. Now in this video, we would like to hold that temperature constant and examine the consequences on a pressure-volume diagram. We can start by establishing three different states of a system. They can be state A, state B, and state C, and you can see that they're drawn at different spots on this diagram. So if this is P2, then state A and B have pressure 2, state C has pressure 1, state A has volume 1, and state B and C have volume 2. Now from that, we can immediately write the temperature of each state. This is simply done using the ideal gas law. So we'll be able to say that point A, or shall we call it state A, is going to be pressure 2 times volume 1, pressure 2 times volume 1, divided by N, divided by NR. And then state B, temperature of B, is going to be pressure 2 times volume 2 divided by NR. Let's just make this algebraically correct while we're at it. And temperature of C will be pressure 1 volume 2 divided by NR. Now, unless A and B or B and C are at the same temperature, which is pretty unlikely because then A and B would have to be at the same place on the graph, or B and C would have to be on the same place on the graph, they can't very well, we can't very well say that those processes are isothermal. There wouldn't be any difference in temperature. But what we could look at is the process from C to A. Now from C to A, we could see that P2, I'm looking at A just at the moment, but P2V1 could potentially be the same as P1V2. These actually could be at the same temperature. Okay, this could be delta T equals 0. We don't know that it is, but it very well could be. The process itself, shown as a perfectly straight line, is probably not realistically at the same temperature. But if you were really, really close together, we don't know what the actual pressures and volumes are. And if this were basically a step in delta P or delta V and it was really tiny, then these could all be at the same temperature. Now let's see if we can draw a graph of pressure volume for the ideal gas law. So we would have, let's see here, P is equal to N times R times T. Because of this software, I'm using X instead of V, but there's something that looks like the graph, and you can see that we can adjust the temperature. Now all of the temperatures are constant here, so this would be a temperature of 140 Kelvin. I can move it up to a temperature of 300 Kelvin, maybe. Oops, yeah. There's 300 Kelvin. And you can see that along this graph, this is pressure, kilopascals on the ordinate, and liters on the abscissa. And so as I move the temperature, the fixed temperature around, that causes the graph to change. So now we've seen what an isotherm looks like on a PV diagram. And we have acknowledged that since delta U is equal to 3/2 NR delta T, and that in an isotherm delta T is 0, that necessarily means that delta U is equal to 0. Now from the first law, we know that du is equal to dq plus dw. Since du is 0, that's going to mean that dq is equal to minus dw. In order for work to be done, there has to be a change in volume. So we can write the work as the negative from V1 to V2 of the integral of P dV. And since we are working with an ideal gas, we can change P to be equal to nRT over V. That's going to give us this integral right here, V1 to V2, of nRT over V dV. And this is going to be an integral we recognize, so we'll pull the constant out in RT, and we'll go ahead and write log V2 over V1, and that's the answer to that integral, so that's the work. Now, notice we have a negative sign in front of work for the heat, and so if V2 is less than V1, this log term is going to be negative. A negative of a negative is going to be positive. And so when we do compression work, we're going to get a positive. Let me see if I can pull up a... All right, here is an example of isothermal work. Now, if we go from V1 to V2, the area under the curve, which is the work, the area under the curve is going to turn out to be a positive number, as is shown here. Now, I can change these on this particular thing. So we will bring the volume there down. We'll bring the volume here the other direction. You can see that now, as we go from V1 to V2, we'll actually be doing an expansion, and in an expansion, the work will be negative. This particular worksheet is online, and there's a link to it given down below in the notes. And it is live online. You can use it just the same way I'm using it. You can also download it and change it. So what we've shown is that in order to work with a pressure volume diagram and solve for work using an isotherm or what all you really need to know is the first law of thermodynamics. The first law is given right here. And then in addition to the first law, you have to know the ideal gas law and a little bit of combination, and you come out with work. And we showed you how to find the area under the curve, which is just this piece right here. We showed you what it looked like. I hope you find this video helpful. Thank you for watching.